we give in to stereotypes. I'll say g'day and you can all say howdy. That's all right, we'll be better than that. Okay, so thank you very much for the invitation. Thanks for inviting me along to this meeting here tonight. One of the parts I love about being introduced is it's quite easy to spot the people who were dragged along here tonight without really knowing what this thing was. Because at the point where they say Dr. Barnes is an astrophysicist, oh, come on. That's not what I was... Nice music, and then you're going to ruin it by letting a guy just science this thing for about half an hour, which I plan to do. So, let me start off by pandering to you with a gratuitous astronomical image. That's going to come back later. I have a friend who's in human resources and was at a conference about human resource managers, and someone got up and revved the crowd up that they really wanted to be a human resource manager. It was a really exciting career. That's really what they wanted to do. I've been to events where astronomers get together and talk about their career, and no one gets up and tells us why we should be astronomers. No one has to, right? Of course you want to be an astronomer. The universe looks like that. Okay? The night sky has been the paradigm of beauty for, as long as people have had eyes. And the great thing is the harder you look at it, the more beauty you see. So if you get a whopping great big telescope and look at something that the human eye couldn't even make out, right? Put a 10-meter telescope on the top of a extinct volcano in Hawaii or something, and you'll see this. Or I should say exactly what this is. Yeah, put a 2.5-meter size telescope in space, and that's what it'll see. Okay. The beauty of the night sky has always inspired us. If you're a theorist like me, if the thing you love about astronomy is all those equations, there's an extra kind of beauty that we see in the night sky, which is the order behind it all. There is this beautiful mathematical order. The idea of beautiful mathematics might be completely anathema to some of you, but it's there. And if you speak that language, then the universe is speaking to you in a very, very beautiful, poetic way. So I want to talk to you about a particular feature of our universe, a particular way the way that it's all put together, and some other ways it could have been put together. Now, to do that, obviously, I'd like to give you a crash course, just spend a little while teaching you the whole of astrophysics. That would be really handy if I could do that, so I will. I need one idea from you, all right? Everyone, brains on, here we go. One idea, equilibrium, that's all I need, okay? Suppose that was a hill. There are two spots there where you can put a ball and it will stay there, okay? You could put it there, or you could put it there, okay? If I've lost you, then the rest of this talk's going to be... never mind, okay. If you put it there, though, if you give it a bit of a nudge, it's going to roll off. So that's what we call an unstable equilibrium, and that one's a stable equilibrium. If you give the ball a bit of a kick, it'll return back to where it came from. So the key to studying a lot of things in the universe is simply to ask, all right, what are the things that can push and pull all the stuff in the universe? And then how can we put them so that they make a stable equilibrium? And that's how we will explain all the stuff that we find in the universe, all the stuff we see in the night sky. So what are all the pushes and pulls in the universe? Here's a crash course in particle physics. There are 4 fundamental forces, and on the next slide I'm going to add 2 more at the bottom, and I'll explain in a bit more detail. All right? So talk on science and faith. You knew what was coming. There's always going to be a bit of science. Here we go. Gravity you're familiar with because you're all stuck to the floor. None of you are floating near the ceiling. That's gravity. Also there is what's called electromagnetism. Sorry to the keyboardist. Electromagnetism is basically whenever you have a charged particle, they will interact with each other. It explains electricity and magnetism. That's all different forms of the same underlying force. You're made of atoms, and the very centers of your atoms are held together by what's called the strong nuclear force. And in certain cases, something called the weak nuclear force will make them fall apart. That's pretty much all we're going to need from those 2 forces in this talk. I want to talk to you about 2 other things at the bottom, which are really sort of ways that the top 4, the main 4, express themselves. So thermal pressure, if you hear about air pressure, all that is this. Okay? The air pressure is just the air bouncing off things. Molecules of air hit the sides of whatever, the window or the wall. That's air pressure. It's just collisions pushing on a wall. If you take a balloon and try to squash it, you push the walls in, and so the molecules hit the sides more often, and so it fights back against you. And that's why it's hard to push a balloon in. Okay? That's thermal pressure. All I need for this last one, called the Pauli exclusion principle, is to say that if this means that things don't like being squashed, quantum things, really small things, things that obey quantum mechanics, really don't like being squashed. That's all I need you to know, okay? If you're a physicist and you actually know what the Pauli exclusion principle is, then great. For the rest of you, in that quantum regime, things really don't like being squashed, okay? That's the whole story. We've got to get through this quickly, right? Let me test this thing out. Let's try and make something stable. Let's try and balance electromagnetism that charged things can hold together versus the Pauli exclusion principle that quantum things don't like being squished. If you put those two things in equilibrium, what you make is atoms. Ta-da! Okay? A number of protons and neutrons you put at the center, tells you what sort of atom it is, and then the electrons go around the outside. Now that's quite important because they have a nice stable orbit around the outside, and if you put two atoms close to each other, the electrons, instead of just going around one nucleus, can sort of go on a complicated path around all of them, and they will bond the whole thing together, and that is chemistry. So congratulations, you're all now chemists. Chemistry can do some pretty amazing things. So you can take these particular elements and make a double helix here and write the instructions for making a person. That's DNA. That's all chemistry. Okay? So here's what I want to say. We're going to do a bit of astrophysics now, and it all boils down to one question. Okay? We want to find the forces in the universe. How can I make them balance against each other? When we're talking astrophysics, we're talking things big enough that gravity matters. Gravity is always attractive. It's always pulling you down, like none of you are floating towards the ceiling. It's always pulling downwards. So the question of astrophysics is simply what's fighting gravity? If we're going to make something stable and gravity is involved, something better be pushing back. And so we can understand all the stuff in the universe as simply what's the thing pushing back. Okay, here we go. If the thing that's pushing back is nothing, then we have a black hole. Right? Gravity has won. It's over. It's done. All right? Here's why we think that there are black holes. This isn't really relevant to the talk. It's just awesome. We are in the Milky Way galaxy. We're surrounded by stars on all sides. We can look towards where there's the most stars. That's the center of the Milky Way. If you look with a radio telescope, you'll find a very bright source where there isn't something there with a visual telescope, one that would work with your eyes. So here's what we can do. We don't see anything there, but we can look really hard with a telescope. And here's a very small bit around the very center of our Milky Way galaxy. All of these are stars. They're not actually that big. That's just the blurriness of the telescope. And what we can do is start at 1995 and keep on watching until pretty much the end of 2016. If you do this on a random bit of the night sky, you'll see all the stars just sort of wander past in one direction or another. But if you go right at the center of our galaxy and have a look, this happens. That is a billion ton nuclear fusion reactor making a complete U-turn in about a month. There is something there, all right? There's definitely something there, okay? From analyzing this, we know it's got about 1 million times the mass of our sun, and we know it's condensed to an extraordinarily small volume, and so there's pretty much no other option. No force we know could fight gravity in that regime. That's almost certainly a black hole. Right? Not really relevant to this talk, but I hope you agree. Pretty awesome. All right, atoms. You're all familiar with atoms, that atoms are solid. So that's the solidity of atoms, right? If you try and push something, it pushes back against you. They're nice and hard. If we fight gravity with the ordinary strength of atoms, what we get is planets. Right? So we can make planets of various sizes. You are here somewhere around the back. There's Earth, and here's everything else in the solar system. Okay, so that's basically a planet. You can make them of various sizes. On the smaller end, they're so small that their own gravity doesn't really matter. As they get bigger, in order to fight off gravity, they kind of need to huddle into a sphere, right? Anything that sticks its head up will get crushed back down by gravity, and so they're all spheres, you might have noticed. The Earth is round. We all, okay, good. If you make something too big, ordinary atoms won't be able to hold it up, and so that extra quantum don't squish me bro comes into practice, and you get what's called a brown dwarf, which are very hard to see. Here's kind of an artist's impression. You may not have heard of a brown dwarf because they don't do very much. They just sort of sit there not being crushed by gravity. The interesting ones are if you go the next step up and you fight off gravity with thermal pressure, and then you've got yourself a star. Now, in order to do that, it's going to have to be pretty hot, okay? Because that gravity is going to be pretty strong, which means that it's going to glow. And in particular, the edge of it is going to glow energy out into space, what we call sunlight. To keep fueling that thing, because it's losing energy, there are nuclear reactions at the center which involve these two things, the strong and weak nuclear forces. So, let me just run through so far. Here's Earth. And north is not up, isn't it? It's quite slightly sideways. Yeah, there's Australia. So there's Earth. Okay, ready? You need to sort of work pretty hard for this one. Take this and, in your mind, squish it down until it's that size. And then there's the rest of the stuff in our solar system. All right, now take Jupiter and squish it down until it's that size. Okay, there's the sun. There's a star called Sirius, and yes, it is that color. Take that, squish it down, and then you have a larger and larger stars. Take Aldebaran, squish it down to there. Is anyone still with me? All right, and then you have, I believe it's pronounced Betelgeuse, and then you have the largest stars out here, which are about 300 times as massive as our sun. Okay, so that looks like a wide range of things, but actually, you know, the universe knows about the limits here. It's those forces in balance that tells us how big these things are. If you're too small, you won't be held up by nuclear reactions and all that. You won't glow. You'll just be sitting there held up by that quantum don't squish me-ness. And out here, you're basically getting to the point where you're too big to be stable. Instead of gas pressure holding you up, it's actually the pressure of light particles bouncing off, radiation pressure holding you up. So, these particularly big stars often happen when the star runs out of fuel and has to kind of rearrange itself to burn something else. Our sun is burning hydrogen into helium. When it runs out of hydrogen, it's going to need to sort of get its act together and collapse a bit and heat up so it can fire up and burn some helium. Here's what happens when a star does a fuel change. All right? This is as mundane as I ran out of something, let me get something else. And that's what it looks like in the universe. This is called a planetary nebulae. It doesn't actually have anything to do with planets, but they are amazingly beautiful. They can look like this or like that. I could do this all night. You really do, that screen's pretty good, but you really do owe yourself like a proper high-resolution screen and a dark room and some Beethoven, a good scotch. Okay, how else can we fight gravity? We can keep things moving to keep them away from the source of gravity. So, for example, planetary orbits. The Earth goes around the sun, as you may have read. So as long as it keeps on moving, it won't fall in. So the motion keeps it at a constant distance from the sun. We can also do this not with this ordered circular motion, but with sort of random motions. Okay? That gives us what we call a globular cluster. They look like this. Each dot on that screen is a star, or so many stars that we couldn't distinguish between them. There's a great quote here from Richard Feynman's lectures on physics, which just says, if one cannot see gravitation acting here, he has no soul. All of the dots are stars. Let me give you a quick simulation about what we think's going on here. This is something that's done in a computer. Here's what we think's happening. The whole set of stars together is sort of acting to pull on every other star. An individual star will be pulled in by everything else, but because it's moving, it won't just all collapse into one blob. It'll sort of carry on out the other side, and so everything just sort of has a nice orbit around the middle here. They won't collide into each other, as cool as that would be, because basically the size of a star, even in the very middle there, the size of a star compared to the space around it is like a grain of sand in a sports stadium or something. So that's not going to happen. That same difference between we can go around in an orderly circular way or we can go around via random motion is writ large in galaxies. So there's our friend again. This is a spiral galaxy. It's not being collapsed by gravity because the whole thing is rotating around one way or another. We know that because if we take one of these galaxies, if we could look at it from side on, no, we can't. It's a bit hard to just wander around the edge of a galaxy. But we do see other galaxies that are side on that look like this. So one side will be going away and one side towards. The whole thing is rotating around to keep itself fighting against gravity. So that's another way to fight off gravity. There's another type of galaxy, which you may not have seen, called an elliptical galaxy, which uses that random motion, except now there's so many stars that we can't pick out individual ones. Right? You've probably never seen a galaxy like this before because they don't usually appear on, astronomy calendars for pretty pictures because they're just sort of a blob of light in the sky. Another sort of entertaining thing behind this. This one's called the Pinwheel Galaxy, and this one's called the Needle Galaxy, and this one's called NGC 1132. Couldn't even be bothered giving it because they'd all be like the blob, the random smudge. Okay. Finally, we're nearly done with this bit. The universe as a whole, why is that not just collapsing under its own gravity? And the answer is that it's expanding. Every time we go and look out at a galaxy in the universe, it's moving away from us, and it's moving away in such a way that if a galaxy twice as far away is moving twice as fast. Now, a very natural way of thinking about that is just stick all the galaxies on, in a two-dimensional case, the surface of a sphere, and then have the sphere expand. But this is not a case of equilibrium. The universe is not sitting still, fighting off gravity. It's expanding to escape gravity. All right, so if you were thinking of studying astrophysics, don't bother, I've just done it all for you. Here we go. What's fighting gravity? If it's nothing, there's black holes. Behold the Rosetta Stone. Okay, some of you laugh. The rest of you need to go home and Google Rosetta Stone. That was funnier than that. Asteroids and planets, it's atoms. If there's quantum degeneracy pressure, it's brown dwarfs, or white dwarfs for that matter. Thermal pressure, you have stars, but you'll need nuclear reactions to stop them from leaking all their energy. Rotation, you have planetary systems and disk galaxies, globular clusters and elliptical galaxies, random motion, and the universe is expanding. Ta-da. Okay. That is basically how astrophysics works. We can take our understanding of the laws of nature as we know them and say, what could I make out of that? And in that way, understand the stuff that's out there in the universe. You may have read, news articles about astronomy, about all the sort of random menagerie of stuff that's out in the universe, stars and quasars and galaxies and white dwarfs and all that sort of stuff. They fit into a coherent scheme because we can understand them using the laws as we know them. And we can do all of this stuff, not just hand-wavy with pretty pictures like I just did it, but with equations to really understand what's going on here. And we do that, and when we boil it down to the basic stuff, we find some numbers there, right? You can take this, make a model of stars and say how big is a typical star, and you'll get an answer in terms of some numbers. Now, some of them will be familiar, like 2 and pi and those sorts of things. And some of them will be simply properties of our universe. Basic things that we don't have any deeper understanding of. They're just there in the deepest laws of nature that we've ever discovered, and that's all we know about them. We can measure them, but we can't calculate them. These are called the fundamental constants of nature, and we can use them to ask, what if the universe were different? What if I took the masses of the fundamental particles, let's make electrons a bit heavier? What if I made electromagnetism a bit stronger, the strength of the forces? What if I changed the way the cosmos as a whole was expanding? What would happen? We don't know why these numbers are what they are, so if we want to think, okay, how else could the universe have turned out? This seems a pretty systematic way of doing that. So, allow me to get started. The reason why these numbers have grab so much attention from physicists is that they stick out like a sore thumb in all of our models. Okay? We would really love to explain these numbers, but they just sit there. So here's another quote from Richard Feynman about one of these numbers, the strength of electromagnetism. He says, all good theoretical physicists put this number up on their wall and worry about it. Immediately you would like to know where this number comes from. Nobody knows. It's one of the greatest mysteries of physics, a magic number that comes to us with no understanding. Okay? So, why do those numbers have the values they do? We can ask a related question, what if they were different? Let me take you through a few things. Let me just remind you what atoms are made of. Okay? Electrons going around the outside, and then in the inside, protons and neutrons stuck together. Actually, protons and neutrons aren't fundamental. They are made of even smaller particles called quarks. And when you get home, you'll either remember that or you won't. Up quarks and down quarks. Okay? So here's what I want to do. Okay? It's just a visual representation of all the other ways the universe could have been. What we're going to do is represent those three numbers. How heavy is an electron, up quark, and down quark? It gives me three numbers. I can represent that as like a point in a block, in a three-dimensional thing. Okay, so here's my block. All right? So how heavy is the down quark? How heavy is the up quark? How heavy is the electron? So if you're going and ordering a universe and you want to order these numbers, just pick a point in there and it will represent our choices for those numbers. So here's our universe. And if I move it this way, I change one of those numbers. There's limits at the top of the bottom that I can go into in a bit more detail if you want to ask me. But basically, there's a range of possibilities there. Our theory tells us what would happen in these universes, and so we can go find out. So if you're inspired by this talk, we can get home and you think, maybe I'll make some universes of my own. Let me give you some help by taking this menu of options, represented in three dimensions, and carving off some of the boring bits that you don't want to bother about. So, for example, steer clear of these two bits, there and there. I've chopped those off because in those there's no chemistry. Hooray. Sorry, I'm a physicist, I have to say. Never mind. Over this side, the fundamental thing, it's a bit like a proton, but not quite. The fundamental particle, right? Okay, I've got the basic stuff. What can I make out of that? I make this particle. What can I make out of this? Nothing. It won't stick to itself or to anything else. Right? Nothing in the universe sticks. All you can do is put an electron around it, and it will have the chemistry of hydrogen, which is to say there's one chemical reaction, hydrogen plus hydrogen makes hydrogen molecule. So if you want to do a chemistry exam in that universe, it goes like this. Question 1, what is the element? Answer, it's hydrogen. It can't be multiple choice, there aren't any other options. All right, question 2, what is the chemical reaction? Hydrogen plus hydrogen makes hydrogen molecule, end of exam. All right, now obviously there's no one there to take that exam because you can't make anything. You can't make anything that could take an exam. Okay? Things are even worse out this side because the only thing that exists out there has the chemistry of helium, which is to say no chemistry at all. Right? That's an even shorter exam. Question 1, what is the element? Helium. That's it. There's no chemical reactions. Bit more help for you. Stick in that region, because if you're not in there, the nuclei will eat electrons, which doesn't help your chemistry very much. Or protons and neutrons, you've got them, but they won't stick to each other. So that's no good either. So stick in that little bit, and then you've got a nice, interesting stuff can happen. You can actually stick something to something else. This is also the fuel for stars, of course, protons and neutrons. So you'll want to stick in this little region here, because if you miss it down here, then you won't be able to form stable stars. Anything big enough to burn is big enough to blow itself to smithereens. If you're up here, you won't be able to ignite any of your stars. Okay? You'll try to squish the star to get it hot enough to ignite those nuclear reactions, but before that happens, the quantum squishiness thing takes over and stops you from squishing it any further. All stars fail to shine. Okay? Or alternatively, there are no stars. Finally, although this one's a little bit more specific, okay? You want to stick in that bit, because in that bit, your stars will be able to make both carbon and oxygen, right? And as you sit there as a carbon-based life form breathing the smorgasbord of oxygen we've put on for you, you should realize that that's pretty important. So here we are in a pretty interesting bit surrounded by some really boring stuff, okay? That, if you have one picture out of tonight, you can either take home the lovely picture of the galaxy, or if you want to think about fine-tuning, have that stick in your mind, okay? whereabouts in this block of possibilities do I get anything that could do anything interesting? And it's pretty much in this tiny little bit here. What happens everywhere else? Nothing much at all. Things don't stick, nothing interesting happens. This is called the fine-tuning of the universe for life. That's pretty much what's going on there. If you would like to be beaten over the head with a very obvious visual metaphor, there's a razor's edge. Is that helping? Okay. I'm a cosmologist. I study how galaxies form, which means that at some point during this talk, I have to show you a pretty video about how galaxies form in simulations. So let me do that for you. It's absolutely essential. So here's what we're going to do. There's always one. Excellent. Fantastic. Okay. Train of thought gone. Who am I? Where am I going? Okay. Here's what we're going to do. Here's how we study how galaxies form in the universe. From our observations of very sort of old light in the universe, very ancient light, called the cosmic microwave background, we know that in its earlier stages, the universe was very uniform, so that it was very smooth. There weren't too many lumps and bumps where this bit was more dense than that bit. The whole thing was pretty much the same everywhere, except for some very small sort of seeds of structure in there. So what we can do is take a computer and program it to actually simulate what's going on there. We take particles that represent a certain bit of matter, and we teach them how to, or we program how they'll interact with each other under gravity, how they'll push against each other due to pressure, how they will glow if they're particularly hot and give out energy. And if they're dense enough, we say, all right, they'll make some stars, and some stars, when they get to the end of their lives, blow up, so we'll put that in our simulation as well. We'll put the whole thing inside an expanding universe and hit play on a supercomputer for about a month and a half, and this is what happens. Basically, the rich get richer. If there's any bit of the universe which is a lump, which has got more stuff than average, it will have more gravity to go and grab more stuff into itself. So the big lumpy stuff gets even bigger and lumpier. So that's what you're seeing going on here. Any bit of the universe that's dense gets even denser. And it's in those places where galaxies will form and stars will blow up and start to blow stuff out into the rest of the universe, which are these explosions you see. And as the movie carries on, the universe starts to form what's called the cosmic web. You have dense bits where there are galaxies connected by thin filaments to other dense bits of the universe. So, by the way, this video is fast-forwarding at the rate of about 1 billion years every 2 seconds, just to put you in the picture there. What we want to do with this at the end of the day, what most cosmologists want to do with this at the end of the day, is to look at the galaxies it makes and see if they look like the galaxies in our universe, and then we see whether what we thought might be the way the universe works could have been right. Okay? What I've been doing is changing the universe. Taking this exact code underneath this one and running it again for a different universe. And in particular, there's a type of energy in our universe that we didn't really predict was there. In 1998, we discovered that the universe's expansion is accelerating. So not only are the galaxies out there moving away from us, they're moving away faster today than they were yesterday. We don't really know why that's happening. The best idea we have is that there's a form of energy in the universe that we call dark energy. Okay? The reason why we would call something dark energy is because we have no idea what it is. That's the only reason you'd call something dark energy, right? Okay? But it has the properties, we suppose, that will make the expansion of the universe accelerate. And as before we looked at that range of possibilities, we can look at the range of possibilities for dark energy, and it's enormous compared to our universe. The number of digits in that number it's 120. That's how many digits. So 10 to the power of 120 is the size of the possibilities relative to our universe. So what I've been doing is changing that number. A bit of a warning, my simulations aren't quite as pretty as theirs. I'm sorry. So here's mine. So here's that same structure coming together, the rich getting richer. There's no dark energy in this universe, okay? And so all the blobs keep coming together. What I'm then going to do over this side is turn up the amount of dark energy. Here's what that's going to do. the time at which the universe starts to accelerate its expansion is going to go earlier and earlier into the universe. Once that kicks off, it's going to be hard for any blob of matter to grab something else because the expansion of the universe is carrying it away. And so basically this whole hierarchical things grabbing bigger things and growing will come to an end. So if we look at over this side, so this bit will continue to grow, and this bit starts to freeze up. It's slightly more obvious if I kick the things up by a factor of 100 now over this side, and that side is pretty much ground to a halt. Time is still going, but nothing much is happening. Whereas in this one, which is roughly our universe, stuff keeps forming. All right? Because they're my simulations, I'm going to show you some more because they're awesome. All right? Let's zoom in. Okay? Here's two galaxies that are going to come together into one big galaxy, but over here, dark energy just makes them separate, and they miss their appointment, and nothing much happens. Okay? And if I go 100 times larger, yeah, nothing much at all. So that's what happens with 100 times larger. I said we've got 120 orders of magnitude to work with here. Okay? So all you need to do is bump it up by, say, 10 orders of magnitude, or 20. And what's going to happen is that dark energy will stop structure forming in the universe before any structure has formed at all. So we talk about fine-tuning for life. Really, this is about whether the universe does anything interesting at all. And in this case, it's really easy to make up a case where nothing much happens. In that universe, or in its cousins with slightly larger values of dark energy, nothing happens because pretty soon everything in the universe is really far from everything else. Right? Everything's been grounded and sent to its room. Nothing goes on. So that is another pretty classic case of fine-tuning. Okay? In a massive range of possibilities, unless you're in a pretty small range where we are, nothing interesting is going to happen at all. So, there's more examples of this in the book that we wrote. There's 6 whole chapters of this sort of weirdness. There's all sorts of entertaining ways of ruining the universe. If you're a supervillain, you'll get some great ideas. All right, we wrote the first 7 chapters of this together. So my co-author is Geraint Lewis, who is a professor at the University of Sydney. We wrote the first 7 chapters together. And now's the time to tell you that Geraint is an atheist. We wrote those whole 7 chapters, and once there's one footnote which begins, at this point, our heroic authors had a falling out, a disagreement. The rest of it's pretty standard. You read the scientific literature about what would happen in these other universes, and it's the stuff I've just presented to you there. That's not really the issue here. The issue is now, what do I do with this bit of information? So here's Geraint's answer, right? He's not here, so I should fill you in. It's a weird idea. It's called the multiverse. Basically, our universe wins the cosmic lottery. If you're waiting for something unlikely to happen, just have lots of goes at it, okay? If you're really terrible at throwing darts and you want to hit that bullseye, just keep on throwing darts. So maybe the reason why our universe got all the right bits for life is because there's loads and loads of other universes out there. And of course, the only universes in which someone's standing there going, I wonder why this universe is just right for life, are the ones which have life in them, right? No one's standing around going, this universe is really terrible for life, okay? This is called the multiverse. We just keep doing a bit more cosmology. For some reason, this has turned up in comic books. I've read a lot of the scientific literature on the multiverse, and Batman doesn't appear anywhere in this literature, which is a real disappointment. I don't even know what Infinite Crisis is, because I'm not a character out of the Big Bang Theory. Why the multiverse? Some of you got that, thanks. Why would we think that this idea is true? Actually, we've got to give it a bit of credit. There's some ideas about how the very early universe works, which might suggest this kind of picture. There's an idea that the universe starts with a very rapid state of accelerated expansion very early on. And in some of our ideas about how that could work, you get a kind of picture where universes like ours form as bubbles, and different bubbles forming in different places in the universe. So those sorts of models are out there. Now, This talk's been weird enough already, so let me just kick it up a notch. Here's a way that this idea could actually be wrong. Right? It's called Revenge of the Boltzmann Brains. Here's the idea. If you're going to be a theoretical physicist, theoretical cosmologist, and say, I've got this idea about how the multiverse works, what you've got is a model of a population of things. So what you should be able to do, at least sort of in your equations, or in your head, is take up your survey clipboard and go around to your different universes, and if you find someone, ask them questions about their universe to see what the typical observer sees out there. Okay. Now, most of those universes are going to be dead, so there's no one to ask, so that's all right. They won't turn up in our survey. But we can at least ask, when we find someone, a question like, what dark energy do you see around you? How much order do you see around you? How big is your universe? Things like that. For certain ideas of the multiverse, and in fact for one of the very earliest ideas of the multiverse, they had a weird property. Our universe, to make us, kind of went to a bit of effort about it. It really put some work in, okay? Starts off, very early universe. I've showed you that whole, that fast-forwarded thing, okay? Very early start, we make galaxies, make stars blow up, they put their elements throughout the universe puts those into planets go around the stars for a while, something happens, I go and ask a biologist, life happens, I don't know what happens in that, never mind. And then, later on, here we are, okay? That's a lot of effort. What could go wrong in your multiverse, and this is not just theoretically, there are some multiverses that do this, is it's much easier to just start off and just make a life form to begin with, because that's one small thing rather than a whole universe of stuff, right? The easiest thing to make might not be an entire universe with order and stars and planets and all of that. It might just be to make a single brain. So if you go around in your head, in your survey, and say, what kind of thing are you? And most of your things say, I'm just a single brain that formed about 2 seconds after the Big Bang. And your universe, your idea has made a wrong prediction, and so it's probably wrong. Right? If you followed all of that, congratulations, you're going to have a wonderful time in the book. And if you didn't, the rest of the book's a lot easier than that bit. Okay? Finally, a fine-tuner, what we're all here for. Obviously, one of the reasons why this bit of science is particularly popular amongst some people, probably a lot of people in this room, is that it makes the universe look like the sort of place that could be created by a fine-tuner. Here's how you might think about that. So the world around us that we see looks pretty well put together, right? The sunlight falls, plants grow, there's nutrients, there's rain, there's the seasons, they make food for us, place to live, all of that's all sort of put together for us. So if you think, okay, my body looks pretty well put together, and we say, oh, your body is sort of, depends on the rules of chemistry, you might start going down, okay, is chemistry pretty well put together? Okay, well, chemistry depends on physics. Is physics well put together? And at that point, you've reached the bottom. Okay, you can go down to the bottom and say, all right, the bottom level of physics are these constants. Do they look like they have been well selected? And the whole point of this talk so far is, yeah, they look like they have been pretty well selected. Against a whole heap of other possibilities, it looks like ours have been chosen for a purpose. So we could think of some chess pieces on their board, trying to work out what the rules of chess are. So they're just sitting there on their board, they watch games play out, and they work out it's a rule of their world that bishops only move diagonally, and they see the other rules of chess. And at some point, one of them might reach the point where they say, all right, here are the rules of chess. And they've done it. They've worked out their own universe. Okay? What I want you to imagine is, imagine we've got there for our universe, okay? At some future meeting of the really important physicist society, Albert Einstein's great-great-great-great-granddaughter walks up to the blackboard, Alberta, and she writes down, I thought that was funny too, but it hasn't been laughed at. Okay, thanks. Alberta writes down some equation on the blackboard and physics is done. We're over, okay? We've basically solved it. Like the chess pieces who have got the rules of chess in front of them. We've just got physics. We've done it, okay? Obviously, we're not there now, okay? Think about those chess pieces again. If they asked a question like, why are we playing chess rather than checkers? They've asked a question that the rules of chess don't answer. Suppose they do something else. Let me go back to the chess pieces, actually. Suppose they start thinking, what about the other rules of chess that there could have been? So there's a particularly interesting case of this. Suppose that you change the rules of chess so that instead of saying, if you know chess, the knight can jump over other pieces, you say the bishop can jump over other pieces, okay? There's a game that's quite like chess in its rules, but not in its strategy, because you can get checkmate after one move. Checkmate, game over. All right? Every game of chess lasts one move. It's no more interesting than flipping a coin to see who goes first. Okay? Suddenly all the complex strategy of chess just collapses down. So suppose they find out, actually, there's something pretty interesting about the rules of chess in this way. Well, we might be facing the same thing when we're staring at Alberta's board. There will still be all the other possible ways that the universe could have been. Now, they might not involve the sort of changes that we've made here tonight with these parameters, but at least that's the best sort of handle we can get on these other possibilities. So what do we want to do when we're faced with a large set of possibilities? Here's the way that typically in science we think about these things, and in everyday life. When you've got a large set of possibilities of things that there could be, what you really want from an explanation is one that really narrows down the range. So here's an example of that. The really good questions are the ones where you end up flipping down a whole heap of possibilities. Okay? Does anyone not know what guess who is? We had this problem the other night. Anyone? No? Okay. So a really terrible question would be, is it a person? Because that doesn't help me at all. A really great question, if you've got a yes as an answer, is do they have both a moustache and a beard? Right? Because if you get a yes for that one, it's Richard. The memory from childhood there. One game of Guess Who that went catastrophically for me. So you're all artistically like filling in the details of that story on your own. Just go with it, that's awesome. So here's the point. We're standing there, we're looking at Alberta's blackboard. We've solved physics in our universe. The problem is, you might want to ask the question, why those laws rather than all the other possible sets of laws? Now, what are the possible sets of laws? Well, one of the hard things about being a theoretical physicist is any mathematical law will do in terms of its known internal consistency. Okay? You could take Alberta's blackboard and fill it, surround it with other blackboards of all the other ways the universe could be, all the other mathematical equations, mathematical structures, mathematical whatevers. Just keep filling up all those other chalkboards, right? You've seen a mathematical library? They're pretty big. Just keep on going. There's all these other possibilities. There'll be one in the middle which happens to describe our universe, but that's not going to tell you why we're not one of the others. What we want from an explanation, if we're going to look for an explanation at this point, is A, it's going to have to come from something that's not described by the rules of science, the laws of science. It's not going to be a physical thing. What we'd like is something that really knocks down all those possibilities. Okay? So if you think that there is a good creator of the universe, what fine-tuning is telling you is that a whole heap of those possibilities get knocked down. Okay? The best handle we can get on that is by changing these constants. So for example, look at the sort of section of possibilities where there's all different values of the dark energy. And then say, all right, mathematically, is there any reason to prefer one rather than the other? Nope, they're all fine. We can describe them. We can even simulate them. That's what I've been doing. Okay? If I then say, what about the theory that the universe has good creatures in it, moral creatures in it, creatures that can understand and love and learn and those sorts of things, and go back to that set of possibilities and flip down all the ones where absolutely nothing at all happens, and suddenly it's looking like a pretty good explanation for the universe. What you get is a universe that's not too similar for ours. That is how I think that this particular argument works. We can understand why our universe is the way it is if we think that it's the creation of a good creator. It really does explain stuff at that level. Okay? Geraint disagrees. So let me finish by simply saying that we spend the last chapter of the book debating this. So I hope that is something that you guys will also do, talking through these interesting ideas. Okay? The book's available outside. We have a special offer. If you buy a book, that's one less book I'll have to carry back to the car. Yeah, $25. So let me finish. I was asked to say a few short things about, just sort of tacked onto the end, of science and faith more generally. So I think one of the great sort of lessons of this particular case is in how you think about the relationship between God and the laws of nature. In particular, I think of it like the relationship between an author and a book. So the laws of nature tell us what stuff there is and how that stuff moved and how that stuff starts off, right? Laws, you know, the stuff and the laws and all that. I think of that, you can think of that in this analogy as being like, you know, for a novel, the plot and the characters and how the story starts off in this illustration. So, you can't replace an author with a character. It's just a different type of explanation altogether. They're just at a totally different level. If you read Harry Potter really hard, you might come up with a fan theory about why one character did something to some other character. What we will not ever do is replace J.K. Rowling with Harry Potter. It's just at the wrong level. Let me turn that round the other way. If there's no God, it's not because we found something in the universe to replace God. The sort of explanation that God is supposed to give to our universe is not the sort of thing any natural thing could do. Okay? So if it needs that kind of explanation, then it must be a God or something like a God. So you can't replace an author with one of the characters. I think this kind of helps. Because often when the science versus religion thing is done, it takes the form of what we really need to find is things in the universe that science can't explain. It's a bit like saying, if we want evidence of the author, we need to find bits of the book where the plot makes no sense. Right? That's not how it works. Right? The evidence that the book has been written by an author is that the whole thing hangs together. Right? Why, you know, or alternatively, the evidence that there's an author is that there's a line missing on page 45 that had to be written in by hand. Okay, maybe that's the author's hand doing something that didn't happen for the rest of the book, but it's not as if the rest of the book didn't need an author either. So what you have to avoid is this idea that here's the things that science explains, the natural stuff, and then here's the things that God does. Okay? I was going to quote this hymn anyway, but this is my Father's world. It's all, okay? All of it. There's the bits that science can explain because God is acting so regularly and by such fantastic order that we can put an equation on it and understand how the whole thing works. There's the bits in our universe that God is doing that way, and if you believe in miracles, there's the bits that don't conform to that, which God would have some reason to do. What you need to avoid thinking is that the way that I find God in the universe is for looking for the bits that science can't explain. Okay? It's all His. Thank you very much.